Assalamualaikum. My name is Pendulum Muhammad, matrix number 88230166, and I represent my group, which is Group 1. First of all, we choose Analyzing the Motion of a Pendulum, a Kinematic project as our title. And as you can see here, our agenda. Okay, now I will start with the introduction. Okay, what is simple pendulum? Simple pendulum is a mass attached to a string of fixed line that swings freely under the influence of gravity. When the pendulum is set to swing, it is discovered that the time swing is constant for a given pendulum length and is unaffected by the bob's weight or size of the arc. A pendulum moves in the swing due to gravity. A body falling freely will experience a constant acceleration from the force of gravity. This acceleration occurs for all bodies, regardless of weight. A basic pendulum swing's time may be estimated using this acceleration represented by symbol G. Okay, move to the theory. Theory can be shown mathematically that the time of swing of a pendulum is given by the formula T equal to 2 pi square root L over G, where G is the acceleration due to gravity. As for additional theory, we found that the pendulum is based on Newton's first law of motion, which states that an object remains at rest, and an object in motion remains in motion at constant speed and in a straight line unless acted on by unbalanced force. Next, a simple pendulum is where a mass is suspended from a point by muscle thread and allowed to swing back and forth in space. The time it takes to complete a full oscillation is L. It can also be defined by periodic motion in the oscillation frequency. Frequency is the reciprocal of its period, which frequency equal to length over time. So it means the frequency is inversely proportional to time, where the mass oscillation at maximum amplitude if it gets shifted out of equilibrium from its equilibrium position. Lastly, F equal to negative kx is the equation if the restoring force is equal to and opposing the displacement of the equilibrium position. Okay, now the objective. There are 3 objectives from this study. Firstly, to study simple harmonic motion. Next, to learn the meaning of periodic frequency and amplitude. And lastly, to learn and understand the concept of simple pendulum.
Hi, Assalamualaikum. My name is Lutful Hakim bin Muda. My number matrix is AA232103. I'll be taking my part for this group presentation for the apparatus part. So basically, this project requires lightest and heaviest pendulum, which is the function of its the heavier pendulum is used to minimize the effects of air resistance and damping, allowing for more accurate measurement of the period, while the lighter pendulum is used to observe the effects of air resistance and damping more permanently. Next, it also needs a ruler. This experiment also requires the use of ruler, which is the ruler is used to measure the length of the pendulum, which is the distance from the fixed point to the center of the mass of the bob. Second last of the apparatus needed in this experiment was the cord thread. The cord thread serves as the suspension for the pendulum, connecting the bob to the fixed point. So, and the last apparatus for this mini project is a stopwatch. So the stopwatch is used to measure the time it takes for the pendulum to complete a set of oscillations in the project. Moving on to our next presentation, which is the procedure. Starting off, the procedure, we start with prepare the pendulum with 2 different weights, and then we prepare a suitable cord that can accommodate the weight of both pendulum. Next, we prepare a measurement and calculation tools such as stopwatch and ruler. And then we start the mini project by using a lightest weight to combine it with the cord and line that is required. By using an appropriate ruler, set length cord at 0.5 meter for the first pendulum. Next, we join the lightest weight with cord taggles so that the cord remains at set length when the pendulum is swinging. And then combine the pendulum with cord tangles so that the cord remains at set length when the pendulum is swinging. Cord tangles must be tightened up until its maximum height, as cord tangles that are not tight will cause an error in measuring the results because the cord's length will likely change when swinging. After the pendulum is tightened up, it is ready to be swung. By using protector, set the pendulum at a head with amplitude about 20 degrees on both either side of the rest position. Release the pendulum at set length and let it swing. By using a stopwatch, record the time for 20 swings of the pendulum. Repeat step 5 until 12 for a pendulum of length 0.45 meter, 0.4 meter, 0.35 meter, 0.25 meter, and 0.2 meter. Repeat the same step for the pendulum with heaviest weight. Lastly from me is that I'll be explaining about the observation. So basically what happened during the experiment. Firstly, we made several observations, which is the timing of the pendulum swings revealed that it took few seconds on average to complete the whole swinging. Second, we also noticed that pendulum swing reached maximum angle of about 20 degrees for its vertical position. Moreover, we also observed a clear relationship between the length of the pendulum string and the period of oscillation. The longer the string resulted the longer periods. The shorter strings lead to shorter periods. And moreover, when we adjusted the mass of the pendulum while keeping the string length constant, we found that the increasing mass prolonged the period, which decreasing the mass shortened it. So basically, throughout the experiment, we also observed that pendulum swing exhibited symmetric behavior, taking approximately the same amount of time to swing from one side to another. And I think that's all from me. Thank you. Bye.
Hello, Assalamualaikum. My name is Ahmad Azib Moshari and my matrix number is A820650, and I will summarize the calculation and result for this experiment. So, in this experiment, we study the periods of pendulum swings, comparing the lightest and heaviest pendulums of the same length. For the lightest pendulum, which is 0.40 meters, the total time for 20 swings was 80.60 seconds, giving an actual period T of 1.508 seconds. Using the formula T equals to 2 pi square root L over G. We calculated the theoretical period. For the heaviest pendulum, which is 0.40 meter, 20 swings to 24.194 seconds, resulting in T equals to 1.247 seconds. Again, we compare this with the theoretical periods. Our results show discrepancies between actual and theoretical periods likely due to error resistance and timing precisions. In conclusion, while the theoretical formula is a good predictor, real world factors like error resistance and mass distribution affect pendulum motion. This experiment highlights the importance of experimental validations and the complexity of physical system.
For the discussion, in our analysis of pendulum motion, several observations and conclusions can be drawn. For the influence of length and mass, we found that the pendulum period is more influenced by its length than by its mass. This can be shown from the experimental data, which the lightest pendulum with a length of 0.4 meters had a period of 1.307 seconds, while the heaviest had 1.247 seconds, showing a minor difference due to mass. For the theoretical versus actual period, the theoretical period calculated using T equal to 2 pi set L over G was approximately 1.27 seconds. Our experimental results were close to this, supporting the reliability of the theoretical model. This finding confirmed that the theoretical prediction align well with the actual pendulum behavior under ideal conditions. Next discussion, in our analysis of the heaviest and lightest pendulum, the trend of increasing period, both pendulums show that the period increased with length. For the heavier versus lighter pendulum, the heavier pendulum has slightly shorter period for the same length, thanks to its greater inertia, reducing the damping effect from air resistance and friction. For the consistency with theory, the heavier pendulum's measurement align more closely with theoretical prediction, providing more consistent and stable result. This insight underline the impact of mass and damping effect and the accuracy of theoretical model. Next, in discussing source of error in our pendulum experiment, there are several factors that could influence the result. First, the air resistance and frictions. These factors can cause minor deviation from the ideal theoretical model. Next, for the measurement inaccuracy. The error in measuring the pendulum's length and timing its oscillation can introduce discrepancies. Third, the human reaction time. Starting and stopping the stopwatch manually affect timing accuracy. Fourth, the angle assumption. The larger initial angle causes nonlinear effect, derivating from simple harmonic motion assumption. And last, for the string flexibility. Stretching of the string alters its effective length, affecting the period. To address this error, we can use more precise timing mechanism, ensure the string remain extendable, and maintain small swing amplitude to better match theoretical assumption. In conclusion, after the trial of a pendulum with a single design, several major propositions were brought into focus. First, for the period of oscillation, we observed that the period or the time for one full swing increased with both the string length and the mass of the pendulum. And for the damping effect, our experiment highlight the impact of damping, where the pendulum gradually loses energy due to friction and air resistance. For the initial condition, we found that the pendulum behavior is highly sensitive to its starting condition, which also affect the period. In conclusion, this result reinforced the fundamental principle of pendulum motion and its behavior under various conditions.